Again, welcome to College Algebra. In these lectures, we're going to cover inverse functions. Our main objective is to understand the definition of one-to-one function, also determine whether a function is one-to-one. Then we are going to verify inverse functions. Then we are going to learn how to find the inverse of one-to-one function. So first, we're going to start with understanding the definition of a one-to-one function. So in this section, we will find inverses of functions that are one-to-one. Again, the inverses of a function that are one-to-one. And a one-to-one functions are normally functions whose inverse are also functions. So let's consider these following two functions. Function one, we said to each student, there corresponds exactly one eye color. This is not one-to-one function because two students can have the same eye color. So to each student, there corresponds exactly one eye color. In this condition, again, is false. It's not one-to-one because, again, we may have two or more students that have the same color. Now, the function number two said to each student, there corresponds exactly one college identification number. Again, this is a college ID number. It's more or less like a social security number. It's normally universities or colleges give a unique number to each student to identify each student. So function two is one-to-one because each student may have a unique college identification number. So that is again the difference, the concept of again one-to-one function. We can see that the function one is not one-to-one function. Why? Because two students can have the same eye color, not one student two. But the second one, two students cannot have the same college ID number. So only one student may have a unique one college ID number. So function two again is the definition of one-to-one function. So that's what we say here. Function two is a one-to-one function because two different students will always have two different ID numbers. Now we know that each element X in the domain of a function should have a single output Y. That's the whole concept here. That's why one student, the output is college ID, have only one unique college ID. So for some function, again, different numbers X in the domain can have the same output also. So we can see from this function here, we have X1 on my left, we have X2, S3, that is our X axis, we have 3 points. Then we have Y. So we can see that in S1, there's a point that corresponds to Y. In S2 also correspond to Y. In S3 also correspond. So this is not a one-to-one function because we can say that three different students, or in this case, S1, S2, S3, have the same output. So it's not one-to-one function. So normally we can use a horizontal line when we have a function as a graph to check whether the function is one-to-one. If the horizontal line touches more than one intersection of the graph, if it touches more than one point of the graph, or if the intersection is more than one, then it's not one-to-one function. That's the whole concept here. So for other functions called one-to-one function, different numbers X have different outputs. So this is one-to-one function. We can see if I draw any horizontal line, it touches the graph only once. So different output for X1 and X2. But let's go to the previous one. When I draw a horizontal line, it touches 3 times. So this is not one-to-one because different outputs, different inputs, S1, S2, S3 can generate the same output. We don't want that. It's like having two or more students having the same eye color. That's not one-to-one. But one student have only one unique ID. Two students cannot have the same ID. Then that's one-to-one. So again, the graph here, we use the horizontal line to test. It touches it 3 times. So that's not one-to-one. If it touches it only once, then it's one-to-one. So here we say a one-to-one function. If we have a function f from a set x, S will be our domain, to a set y, which is our range, it's called a one-to-one function if and only if different numbers in the domain of f have different outputs in the range of f. And that's the graph we have here. Different x, we have s1 and s2, they have a different range or y value different. So again, testing with horizontal line, it touches on the graph only once. But as we said earlier, the previous graph is not one-to-one function because when we draw the horizontal line, it touches 3 times, which means S1, S2, S3, we generate the same output. We want one-to-one function means one X1 should generate its own output. S2 should generate its own output, not to generate the same. Again, as we said in the earlier example, students assigned to eye color is not one-to-one. Why? Because 2 students can have the same eye color. But student to college ID number is a unique number, so it's one-to-one. Each student can have only one type of number. So now next, we're going to determine whether a function is one-to-one. So again, in our first objective, we understand what is one-to-one function. We get the definition. Now let's go through the steps how to determine whether a function is one-to-one. So here they give us a function, 2 functions. We have f at s equal to s to the power 4 plus s squared. B f at s equal to s cubed. Here we want to determine whether each of these functions is one-to-one. F at x, I will look the exponent is 4, which is even number, which means if I use 2 and -2, I'll get the same answer because 2 squared will give me 4. -2 squared also will give me 4. But here, we only get one value. So here the solution said the function f at x equal to s to the power 4 plus s squared is not one-to-one function because different numbers in the domain will have the same output. If I have -2 and +2, they are different 2 input values or the domain, the x values, but they are going to generate the same output, which will be 20. Because any time the exponent is even number, when you have a negative value, square is positive. So 2 square is 4. 2 square is 4. -2 square, so what is 4? But the second B, the function f at s equal to s cubed is one-to-one. Because if I put 2 here, I will get 8. If I put -2, I'll get -8. So I'll get different values for each input value. So as we said earlier, we also can use horizontal line test to determine whether a function, in this case, the function is a graph, whether it's one-to-one or not. So in this example we have here, this is a one-to-one function. Why? Because the horizontal line touches only once, which means each x value or the input will generate different outputs, unique number of outputs. So we have only one intersection horizontal line. If you have more than one, then it's not one-to-one. Now, next, they say we should determine whether a function is one-to-one again. If we are using horizontal line here, now we can see our function here. We want to determine if it's one-to-one. When we draw the horizontal line, it touches it 1, 2, 3. This means if I have 3 different input values, they are going to give me the same output value, which means it's not one-to-one. One-to-one means each x value, which is the domain or the input, will only generate unique one y value or the range. But here we have three domain x values generating the same output. So this is not one-to-one. We can go back once. This is one-to-one. Why? Because we used the horizontal line to test. Intersection is only once for each horizontal line. This means every x generates only one output, different output. Each x value generates different output. So now let's go to the next section, which teaches us how to verify inverse functions. So for example, we have a figure A here, which illustrates a function f from the set of x and y. The set of x is on my left side, the set of y is on my right side. Now, since we have three arrows pointing to a single y, we will say that the function f is not one-to-one, because here it means that we have three inputs, S1, S2, and S3. They are generating the same output. They are not unique outputs. So this is not one-to-one function. Now, if the arrows in figure A were reversed, the diagram will not represent a function, which means if we reverse it, we're going to have the same input, but they generate three different outputs. Then that's not representing a function. So a one-to-one function means each x will generate its own unique y value. But in this case, it's not one-to-one, but it's still a function. If we have three different inputs and they are generating the same output, it's a function, but it's not one-to-one function. One-to-one function is each input should generate its own unique output. Now, if we have the same input generating different three outputs, then totally is not a function. And normally we check if a function is not a function by graph using the vertical line test. We use the vertical line. So when we draw a vertical, let's say we have this function here, let's go back. If I draw a vertical line here and it touches the graph more than once, then it's not a function. It means we have one input generating two different outputs, because a vertical line means we have one input, x. Now, if it touches twice, it means it's generating different two or more outputs. So always we use the vertical line to test whether a graph is a function. Then we use horizontal line to test whether a graph is a one-to-one function. So let's keep going now. Here now we said that if the arrows of the one-to-one function f in figure B, this is one-to-one function y, each input x1 generates its own output, each input s2 generates its own output. So this is one-to-one function. So here we say that if the arrows of the one-to-one function f in figure B were reversed, as in figure C, the diagram will represent a function. Now, this function is called the inverse of a function f and is denoted by symbol f raised to the power -1, which represents inverse of a function f. And this is our main topic for, again, this section, which we're going to cover. So what is an inverse function? If we have f and g, we have a function f and g, and they are two one-to-one functions, such that f composite g at x equal to x, which means if I put g at x inside f, my answer should be x. For every x in the domain of g, and also g composite f is also equal to x. So if I put g at x inside f, which means f composite g at x, the answer should be x. And the same way, but if I change the direction and I put f inside g, the answer also should be x. So f inside g, f composite g, and g composite f give us x. So every x in the domain of the function, then we will say that f and g are inverse functions. So function g can be denoted as f inverse. It's because we have a function f. So g will be inverse of f, which we call the inverse of f. So we're going to see example now. So this is our first property. We say that if f, a function f, is one-to-one function, then there's one-to-one function of the inverse of the function f, such that the inverse of f function composite f at x will give me x. And also f composite the inverse of function f at x also will give me x. So if these two hold, then we have what again we call the inverse of the function. So property 2 said the domain of the function f is the range of the inverse of the function f, and the range of f is the domain of inverse of the same function f. So with these two properties again, we can be able to find the inverse of a function. So let's try this example. Here we want to verify they gave us two functions, f at x equal to s cubed and g at x equal to square a cube root of x. Now our goal is that we want to see if these two functions are inverse. So we know the property. We find the composite of f and g. The answer we get, we find the composite of g and f also. If the answers are the same, then the two are inverse. So that's what we did here. We find the f composite g at x, which will be f inside g at x. So anywhere we see x for f at s, we replace it with g at s equation. So our function is only s cubed. So we are going to represent s cubed. S cubed will be square cube root of s cubed. So we have the s cubed, which is what we have. But anywhere we see s, we will replace it with g at x, which is cube root of x. So you can see here, we put the cube root of x and then the cube, because we need to keep this cube. We are just substitute the x here. So x here become cube root of x. So we get cube root of x to the s cube, and that gives us x. Now let's try the opposite with g composite f at x, which means this time we are going to put f at x inside g. So we're going to substitute. So my g at x is cube root of x. So anywhere I see x, I'm going to substitute with s cube. We're going to keep our cube root. So, and now I have s cube, then the cube root also give us s. So since both of it, both composite, f composite g at s and g composite f at s give us x, we can conclude that f at s is the inverse function. The g at s is the inverse of f at x, or f at s is inverse of g at x. Now, so here we say because g is the inverse of f, we can inverse notation and write g at x cube root of x as f inverse at x, which equal to cube root of x, because again, f is the inverse of g. Then we can also use the inverse notation, right? F at s is s cubed as g inverse at x equal to s cubed also. So that's the property we use, the composite property, as we said. Property 1, I have two functions. I want to, here we are verifying, we are not determining. In our next section, we are going to learn how to find an inverse of a function. In this section, a function is given to us, two functions. We want to know if the functions are inverse of each other. And these are the two properties must hold. We find the composite of the first function and the second function. If it's x, we do the opposite way, f inverse. If it's also x, then we say the two functions are inverse. This is to verify. So we saw this example. We have f at s is s cubed, g at s is cube root of x. So we're going to find the f composite g at x, then g composite f at x. If both answer is x, then we say the two functions are inverse. Now, in the next section, we're going to learn how to find the inverse of a one-to-one function. So this is the strategy. The strategy for finding inverse of function f if the f at s is given, the function f is given. First, we are going to replace f at x with y. Then we are going to interchange the variable x with y. Then we find the y. The answer we get will be the inverse of that function. So again, one more time, we have a function f at x. We just change the symbol f at x to y. Then anywhere we see y, we give it x. Anywhere we see x, we do y. We replace it with y. That's step 2. Interchange the variables x and y. Then after that, we solve for y. Then the answer we get will be the inverse of it. So we replace y with the inverse of the function. So let's do it. So here we have f at x equal to 3 by 2x plus 2. And we want to find the inverse of this function and verify our result also. Verify the result means we will do what we did previously with the two properties. We find the composite of the first function and the second, and the composite of the second function first. If both answers give us excess, then we say they are inverse. But here they give us only one function, and they say we should find the inverse first. Then when we have two functions, we can do the verification as we did in our previous example. So the first thing we're going to do here, we're going to replace f at s with y. And that's what we have here, y equal to 3 by 2x plus 2. Then anywhere we see y, we will replace it with x. And anywhere we see x, we will replace it with y. That's the inverse. And that's what we have here. So s equal to 3 by 2y plus 2. Now we need to solve for y. So we follow the process here. 2, again, we go down. First of all, we find the LCM. So this will be 4 now, because this is divided by 1. And it will be 2. This will be 3y plus 4. Then the 2 can go to the left across the equal sign. So we get 2s equal to 3y plus 4. And then we take the 4 to the left. It's positive. So when you cross the equal sign, it becomes negative. So we get 2x minus 4 equal to 3y. Since 3 is multiplied by y, when you cross the equal sign, it's going to divide. So y will give me 2s minus 4 divided by 3. So we almost finished. Now what we do is that we'll replace y to be the function f inverse. So this is the inverse of the function. And that's what we have here. That's it. So if a function is given and we are looking for the inverse of it, the first thing we do, replace the f at s with y. Anywhere you see y, replace it with x. Anywhere you see s, replace it with y. Then find the value of y. If you can be able to find the equation for y, then you have the inverse of the function. That's it. Now, the next step, we want to verify it. So we have to do the same thing we did in our previous example. To verify a result, now we have the two functions. So find the composite of the first one and the second one, then the composite of the second one with the first one. So I will say the function f composite f inverse, or the inverse of f. Then the inverse of f composite f. So here, since we know that the inverse of f is 2x minus 4 and 3, the function we have, anywhere we see x, we'll replace it with that value. And remember, our function is 3 by 2x plus 2. So the x, we replace it with the inverse of the function, which is 2x minus 4 by 3. We do the calculations here. Our final answer will be x. Then we do the opposite. Remember, f at s is 3 by 2, x plus 2. And the inverse of it was the 2s minus 4, 3. So now the inverse will be outside, then the function will be inside. So anytime, anywhere I see x in the inverse of the function, I will replace it with 3 by 2s plus 2. So this is the only x here. So we get 3 by 2s plus 2 minus 4 all divided by 3. And that's what we have here, 3 by 2x plus 2 minus 4 all divided by 3. With the 2 is the original part of the function here. So we solve all this, and after all the arithmetic operations, we get x. Okay, so we are right. And the original answer we get for the inverse of the function, which is 2x minus 4 divided by 3, is correct because both composite give us x and x. Now, because we can interchange the position of x and y to find the inverse of a function, we can also say that the point BA will lies on a graph of y equal to f inverse at x, the function f inverse at s, whenever the point AB lies on the graph f at x. So what we are saying here is that's almost like, I would say, what a reflection. Since f at x, the inverse of it go opposite, we change s and y. If we have a point BA and is the inverse, then the original function point to be AB. It's like we are, because remember, when we have a function, to find the inverse of the function, we'll replace x with y or y with x. That's what we did. So here means, remember a point, the first value will be A. So let's say A is x and B is y. If I'm finding the inverse of the function, anywhere I see x, I'll replace it with y. Anywhere I see y, I'll replace it with x. So the point will lie at B and A. For the inverse of the function will be B and A. If the original function point is A and B, lies in A and B. So let's try one more example. Here they say we should find the inverse f at x equal to s cubed plus 3. Then we should grab the function and its inverse on the same set of coordinates. Here, I didn't grab the function because if you use the calculator, again, you can easily graph it. Just press graphical calculator, enter the function, and you get it. Or you can come up with any possible points, then you graph it manually. So you set a table with a different x value, find the y, then because you have the both inverse function and also original function. So you're going to have the two tables for both. And we'll see how the A and B line. It's kind of like a reflection mirror image. So here we say to find the inverse of this function, the first thing we do, again, as we did previously, replace the f at s with y. Then secondly, anywhere I see the y, I'll put x. Anywhere I see s, I'll put y. Then I'll look for the y. The answer I get for the y will be the inverse of the function. That's it. So let's go. We have f at s equal to s cubed plus 3. So we change f at s to y. Now, anywhere we see y, we put x. Anywhere we see s, we put y. So here we get x equal to y cubed plus 3. Now we need to look for the value of y now. So s minus 3 equal to y cubed. So y will give me the cube root. When the cube cross equal sign, it becomes cube root. When the cube root cross equal sign, it becomes cube. So y will give me cube root of s minus 3. So this is, again, my inverse of the function f. So the inverse of the function f will be cube root of s minus 3. Now the next step is to plot the graph. Again, you can use the calculator to do that. So again, this will be the end of our lectures. So in these lectures, the most important thing we learn here is how to find an inverse of a function And also if you have two functions, how we can verify if the two functions are inverse of each other. So again, wish everybody the best and thank you.